Well, good afternoon, everyone. My name is Umar Wani. For those of you who don't know it, I'm an assistant professor here at the Department of Civil and Urban Engineering. And it's my pleasure to welcome today Professor Taha to the Professor Ahmad Taha to the C2 Smarter seminar series. Professor Taha is an associate professor in civil and environmental engineering at Vanderbilt University, Tennessee, with a courtesy appointment in electrical and computer engineering at the same university. He holds a PhD in electrical and computer engineering from Purdue University, Indiana. Before joining Vanderbilt, he was an assistant professor at the University of Texas, San Antonio, and was also a visiting researcher at Argonne National Laboratory, MIT, among other places. His research spans dynamical system sciences, control theory, optimization, and cybersecurity with application in energy, water, and transportation systems. And that's why we are here today. Well, without further ado, I just want to say thank you, Ahmad, for joining us, and the floor is yours.
Thank you, Ahmad, for the invitation. Pretty easy, maybe. Is it my movement? Or maybe?
Can you try that?
Yes. Much better, maybe?
Oh,
yeah?
Yeah, maybe just like...
Put it in my pocket?
Yeah, in your pocket.
Okay, hopefully that will happen. Thank you. Thanks, Ahmad, for the invitation, and thank you for having me here. Today I'll be talking about control engineering problems in smart cities, and I'm hoping that this talk has a little bit of something for everyone involved. Let's start right through it. Today's talk is about how we should be managing and controlling and monitoring our future infrastructure. We know for sure that future infrastructure will be extremely difficult to manage. We know that they will be very uncertain. We also want them to be carbon-free and resilient. We know from the 2021 ASCE infrastructure report that our infrastructure kind of sucks, has a grade of C-, so we need to do better. And we are also aware that the world still invests a lot of money in urban infrastructure. The world basically invests $3 trillion a year on major infrastructure, and still not enough. So we know we need to be spending a little bit more on our decaying infrastructure. Urban population growth requires a lot of integration between infrastructure. We need to make our infrastructure more interconnected, smarter, more advanced. We need to add more policy, more regulations, but also we need to add more theoretic foundations, which NYU and this department does a lot about to advance. And hopefully, in the next few decades, we will see a complete shift in infrastructure from being static infrastructure into dynamic ones that are carbon neutral, that are cost effective, that are robust to worst case uncertainty, and so on and so forth. These are all examples of what's going on in over the past few years in our infrastructure. We know that we haven't done enough to curb carbon emissions, so we need to start building bigger and more resilient things again. We also know that the investments in renewables, although they've been increasing, they haven't increased to the extent that we can actually meet carbon offsets and the carbon reduction that we anticipate and that we require. We also know that the carbon dioxide in the atmosphere has reached its substantial peaks, so a lot of crazy figures and a lot of worrying trends. There's also problems in water systems with forever chemicals and PFAS contamination, so that's another issue that sort of extends beyond the carbon footprint of other infrastructure. And we also know that Americans spend so much time on the road, so everywhere you go, you're faced with substantial challenges which give academics like myself and other folks a lot of work to do. In general, there are four major ways to address all of these issues in today's infrastructure. And these solutions can be categorized into four different solutions. The first one is policy-driven. So governments or system operators and stakeholders decide that we're going to have to enforce a new policy to curb emissions through taxations or through tolls and so on and so forth. So that's the first sort of level or plan of attack to address these issues. The second one is investment, building more stuff, building more solar and wind farms, building more batteries, building better reservoirs and so on, adding more lanes sometimes, which can be controversial for the transportation folks. So this is the second solution. The third solution is through incentives, using game theory, using economics, using mechanism design, incentive design to change people's behavior. And the fourth one is through theory, design better control algorithms to already manage today's infrastructure. So assuming we don't want to do any of the three, how can we come up with new theory to improve today's infrastructure? And my group's focus is mainly on number 4. This doesn't mean that the first 3 are not important. These strategies are all complementary and they are all required to advance our infrastructure in cities, but my group focuses mostly on number 4. It is argued that $1 in infrastructure investment yields $3 in GDP growth. This figure is can be a little bit dubious, as some studies have shown after this came out, but still there's definitely a net positive improvement in the GDP when we invest in our infrastructure. But also it's important to note that not every dollar we invest is created equal. Basically, a dollar that we spend on policy or investments or incentive has arguably a lower yield than a dollar we spend on a new control algorithm or a new smart method to manage traffic on a highway, right? So I'll reiterate, my group's research focuses on creating computational algorithms for urban infrastructure, and this is what the talk will be about. My group tries to develop the balancing of the development of new foundations with applications. So I'm interested in 2 things. I'm interested in new theory and understanding why things work and how they work, but also I'm interested in applying it to realistic models and infrastructure in energy, power, water, and transportation. The themes that we'll be focusing on today are uncertainty, either human-driven uncertainty or system-driven uncertainty, nonlinearity and the physics and the governing laws of physics in water, energy, and transportation, scale, and performance guarantees. I'm interested in an algorithm that works under certain non-restrictive assumptions or conditions, and I'm interested in understanding why it works more than whether it works or not. And we will be covering these four themes. We will be talking about climate change-aware algorithms for energy systems. We will talk about contemporary problems in drinking water systems. We will also talk about mobility and transportation, as well as multi-infrastructure problems. So I won't have time to talk about number 4 as much, but there will be a little bit of the first 3 bullet points, basically. The major technical challenges that I will be addressing in this talk and that most of my PhD students work on are basically one of these 4 challenges or all of them combined. First one is the lack of mathematical frameworks. Sometimes in many infrastructure models, there's a lack of system-theoretic understanding of what's happening as a whole in the system itself. There's also significant time scales discrepancy, meaning that there's multiple time scales involved in the decision-making problem in a specific infrastructure. Most of the dynamical models, most of the physics-based models that govern the laws of physics in transportation and power and energy and water are non-convex and nonlinear. So optimizing the performance can be very tricky and challenging. And the 4th theme is the rampant uncertainty. There's uncertainty from human-centered conditions, from weather conditions, from parametric uncertainty, and so on and so forth. So these will be the 4 things that we will discuss today. And before we go through the discussion of what I'll basically be talking about, there's a core area of science involved, which is control theory. So even if you haven't heard of dynamic system theory or control theory, or you come from a very different background, hopefully this slide should give you a super brief crash course on control theory in maybe a minute or 2, all right? And during the talk, if you have any questions, just please feel free to raise your hand and ask me. It's meant to be an informal talk, so please don't hesitate to ask questions. So, control theory is the study of dynamical systems. Anything that moves in space and time, we label that as a dynamical system. This could be as simple as moving a chair or a table, but ideally as complicated and as important as moving an infrastructure from one point in space and time to another that is desirable. We will be defining that shortly. And dynamic systems in control theory can be modeled in 2 different ways. I have inputs U and outputs Y, and I will be sticking with that terminology during the presentation. Anytime you find a quantity U of T, this means it's a controllable input of the system. And anytime you see a Y, this means this is an output of the system that is measured by a sensor, right? So the first way to model dynamic systems is through input-output mapping. You have inputs, a vector of inputs and a vector of outputs, and basically you have a mapping that is data-driven. You don't know much about the physics of the system, you are only interested in recovering the mapping calligraphic F in the slide. So this is one way to model dynamic systems, and this is one way to potentially do control theory or to adjust your controls to meet a certain output performance. The second approach of modeling dynamic systems is through differential equations and partial differential equations, basically relating the output Y through a physics-based model related to the inputs and its many derivatives. Okay? So we call the first one data-driven approach, and the second one physics-driven approach of modeling dynamical systems. Most of the talk, actually, all of this presentation will not be about data-driven modeling of dynamical systems. It will be about physics-based modeling of dynamical systems. And we'll have good reasons as to why we're doing this. The fundamental questions that any control theorist or any control engineer asks are as follows. So as someone who's interested in dynamical systems theory or control theory, you always ask one or all of these questions in your system. What is a good model? What makes this calligraphic F or little f a good physics-based model? What distinguishes a good model from a bad model? We know all models are wrong, but what is a good wrong model and what is a bad wrong model, right? When do you select data-driven modeling versus physics-driven modeling? Very, very fundamental question at the essence of dynamic system theory. And when is the system well-behaved? Meaning, is the system stable? Is the system gonna go crazy if I inject a certain control input? So questions related to stability are very important. And third, a more applied question is how can we design a better control U of t to make Y of t smoother or safer or cheaper? Basically, how do I do the control of the system? And this means different things in different infrastructure. Many of these questions are theoretical indeed, but they are all applied to critical infrastructure problems that we will discuss. And this would have examples in climate change, flood control, traffic reduction, and so on and so forth, right? So basically, the entire talk will be about finding these models and how do we use these models to find a better U of t to make Y of t, my data, my sensor output, my measurements, behave in a better way, whether it's in transportation or water, and power systems. So more of a tutorial than a list of contributions. The talk will come to you in 4 parts. The first part is some control algorithms in transportation systems. The second part, which will be the longest of the 4, the second part will be on drinking water systems. Basically, how do I control hydraulics and water quality in drinking water systems? The third part will be about stormwater systems and how do we regulate floods or control floods in real time when they happen in urban environments. And the fourth part is a new set of theory, a new set of math for renewables-heavy power systems, where most of the power that's coming from energy systems is generated from fossil fuel resources such as solar and wind. Any questions so far? No? Good? Right. So as promised, the first part will be related to transportation. We know that America loves cars. Anywhere you go in the world, you see fewer cars than here. And I'm sure most of us are aware of the history and the politics of why Americans love cars, right? But basically, this is the state of mobility in the US. Congestion costs around $80 billion a year, which is a lot. It also causes 19.8 million vehicle crashes, which is a crazy number when I read it. I tried to make sure that there's not the period is actually well placed in the 19.8. So basically, a giant number of cars are involved in crashes every year. And so many fatalities and a lot of delays and so on. And 28% of total energy consumption is on transportation systems. So major issue if you want to transition towards carbon-free society, and this is why transportation occupies a central theme in the modern discourse. Motivation here is basically that tech can indeed reduce, technologies can actually reduce crashes, congestion, and emissions. And maybe we are not in need of Musk et al. To rescue us from, to rescue us with their full self-driving technology. Maybe there's already technology that's really good enough for us to use to transition towards electrified transportation and fatality minimal transportation systems. The basic argument or the basic thesis is that small fraction of cars that are connected and autonomous vehicles, plus some sensors, plus a lot of smart control algorithms can end up reducing emissions, can end up reducing the number of fatalities. So basically a lot of control in transportation can improve a lot with very limited investment. These are the high-level objectives of freeway traffic control. The first one is ensuring traffic flows at maximum capacity. So if you have a system that you've built to house a certain capacity, and the quality of the system doesn't diminish substantially if it's operating at capacity, ideally we want traffic systems to be flowing at maximum capacity with limited congestion, okay? Specifically during rush hours. And there's been so many control algorithms over the past 3 or 4 decades in transportation systems to improve traffic. Examples include ramp metering, tolls, variable speed limit, connected and autonomous vehicle controls, and some of these have already been implemented in today's society, which is great, right? So it's nice to see some simple control algorithms being implemented in our cities and on our highways. Arguably, CAV control is probably the cheapest technology, but the downside of it is that it requires a lot of math and engineering, and it also requires the willingness of the system operator to take a risk of actually implementing an algorithm that an academic wrote in a transactions paper. So, but arguably it's the cheaper because if you have a couple connected autonomous vehicles on the road, they can give you a lot of benefit to reduce congestion. This is what this portion of the talk will be about. Before we talk about CAV control, let's talk about VSL control, which is variable speed limit. Basically, putting signs on the highway that tell people to abide by a certain speed limit, which is lower than the speed limit, the usual speed limit. And there's issues with VSL control, which are basically that it relies on compliance rates. So the nice math and the nice theory that you derive from VSL control mostly works when everyone's complying or when most people are complying with the posted speed limit, but no one actually complies with the speed limit, or more than 80% of the people do not comply. But there's actually a lot of recent work on coming up with theoretical guarantees when half of the population doesn't actually or don't actually abide by the posted speed limit. So it's a very active and interesting research field. Something that I want to notice about VSL, because we have implemented VSL in Tennessee on a couple of highways, the thing that we noticed, even when we post a variable speed limit sign that people do not abide by, in the period of time when that variable speed limit controller was posted, there has been a significant reduction in accidents on that same highway stretch over a significant period of time. So, from a control engineering perspective, of course, we want people to comply and so on, but from a society-based perspective, this control algorithm, even though the way the number was generated is so complex and so on, it resulted in great societal improvement. So, people are not complying, but the outcome was still that there's been so much reduction in fatalities. And maybe it's because those who drive recklessly maybe slowed down a little bit and so on. There's a lot of societal components that we do not understand in why VSL actually works. But this talk is not about VSL, this talk about CAV control. The scope of this work is to design real-time controllers for CAVs considering capacity drop. So capacity drop is this phenomenon that happens when there's congestion on the highway. And basically we want to take one of the most advanced traffic nonlinear models and do CAV control, and we want to do CAV control in a very efficient way. And I'll explain what I mean by CAV control in a little bit. Basically, we want to control CAV platoons as drawn in this image, and CAVs act basically as moving bottlenecks. So if you predict there's going to be major congestion downstream, you want the CAV platoon to be aware of the predictability of that congestion happening downstream and basically driving or guiding the cars between them into a specific speed so that you get a significant reduction in the downstream bottleneck. Okay? The major control variable that we'll be talking about here is the speeds of the CAVs in space and time. So in space and time, what is the speed that I want my CAV to have, and the car doesn't really need to be equipped with very sophisticated technology. It could be as old as someone just receiving a signal and driving at that posted speed limit manually, or it could be through adaptive cruise control, right? So it doesn't really require that much technology, which is a nice thing about this. There's a lot of literature on this topic that I'm not going to go through because I really want to get towards other topics in this presentation and give something for everyone. But basically, there's been a lot of control algorithms to solve this problem in the literature, and some of them are based on PI, and PI is a proportional integral control algorithm that seeks to minimize the error, which is defined in terms of a linear and an integration component of the tracking error of the system. MPC is this model predictive control algorithm that tries to optimize also for the system model, for a coarse system model representation. So there's been a lot of work. The issue with this work in the literature is the fact that a lot of it is not computationally efficient, or a lot of it requires a lot of tuning, or a lot of it requires real-time optimization, and so on. So this adaptive linear quadratic regulator, which is another control algorithm that we have specifically tailored and derived and designed theoretically, sort of addresses these issues in the literature. Also, most of the studies have been performed on macro simulations, and macro simulations are not very detailed models of what's happening on the highway. So ideally, we want to do these control algorithms or implement them on very detailed micro simulations and get data from the highway. So these are the objectives: are to design efficient controller with performance guarantees. Again, we're not interested in just designing a controller that works. We're interested in designing a controller for the CAVs that works under certain conditions, and we want to know why it works, when it works, and why it works, and when it fails to actually work. So we're interested in what we call performance guarantees, just knowing when things work and when things won't work. And also the other objective is to test the controller on micro simulation and macro simulation as well. So this is basically the problem statement. The CAV traffic control problem, even if you've never worked in transportation, this should give you like a brief introduction to what is the connected and autonomous vehicle control problem. It's basically adjusting the speed of a car that someone's driving to mitigate traffic downstream, okay? And that's it basically, subject to some advanced models of traffic, subject to some data and measurements that you're getting from the system operator, and that's what the CAV control problem is, adjusting the speed of the connected autonomous vehicle that has been put on the highway by the city operator or the transportation system operator in a certain city. Mathematically, this problem can be written as follows. We want to minimize a certain cost function in terms of the state of the system and the control input, the state being x, the control input is u, subject to the nonlinear dynamics. And the nonlinear dynamics here delineate two things. One, the physics of the car, basically the position and the velocity of the CAV of the car itself that you're trying to control, but also a detailed model of the traffic densities on the highway. Furthermore, another control input is u of k in calligraphic u, which means basically my control input of the car is bounded. I can't set an arbitrary speed. The speed increments of my CAV need to be slowly adjusted, and so on and so forth. And the system states here, again, are basically the densities on the highways and the CAV states. The cost function minimizes some operator-driven cost function to make sure that, to penalize congestion, to make sure that changes in the speed of the CAV are smooth and not crazy, and so on. So this is basically the control problem. Basically, you have a cost function subject to physics and subject to other human-driven constraints or car-driven constraints for the CAV. The approach that we follow to solve this problem is through an iterative linear quadratic regulation where you don't need optimization. Basically, we have an approach where we solve P by actually not solving P, which is the novelty here. You can take this to any optimization solver of your choice, but the problem will be non-convex and it will be super slow to solve, right? So ideally, you want to solve this, but you can't solve this in real time because the problem is convex and you have so many states, and the nonlinearities are really tricky for traffic models, so you want to find proxies to solve problem P. More detail, this is what the dynamics of the traffic, of the traffic densities and CAVs are. Again, the state vector collects all the traffic densities rho on different highway segments, as well as the positions P1 through P and CAV, the positions of all of the CAVs that you have at time K. The control inputs are, again, the speeds of the CAV platoons. So each platoon should ideally have a speed, and this is what the control input that you're solving for. So this is the thing that we want to produce to the guy or the lady who's sitting actually in the car. The objective is to design a simple feedback control K that looks like this. And in dynamic system theory, this is one of the simpler control laws. And this control law or control algorithm tells you basically two things. One, measure x of k in real time, measure the state of the highway in real time. And the state of the highway is nothing but the state of the traffic densities on the highway, which if you have a lot of sensors, you can deconstruct or compute, in addition to the state of the CAV. But you're sitting in the CAV, so your state is kind of with you. The second thing that this control law tells you is to compute a gain k as a function of little k to make sure that this problem that I've explained earlier is actually solved. And this is what we do here. We find a way, given the nonlinearities of the system, given the highly nonlinear system dynamics, to find k that changes iteratively in a very computationally efficient way with some performance guarantees and some metrics that we optimize for. And this k gain also implicitly penalizes uncertainty in the system or takes these model uncertainties and makes sure that the system is robust against them. I'm not going to go through the detail of the algorithm. It's going to take like 20 minutes and there's no point. So if you're interested in the algorithm, you can find it in the paper. But basically, the algorithm is just a detailed linear quadratic regulation, which is a very famous control approach, changed and modified to meet some performance guarantees for the nonlinear systems. Great. We have done two sets of simulations on macro simulations and micro simulations, and we have compared with the approaches in the literature, and we have utilized metrics in the literature that tells us how good the controller is behaving. Okay? I'll spend a few minutes just explaining what's going on here. So basically, for the macro simulations, for the very coarse macro simulation that isn't concerned with individual vehicle dynamics, so just the macro simulation depicting the traffic densities on the highway, we set up an 8-kilometer long highway stretch, and we have a duration of 2 hours with 10-second time steps, could be reduced if needed. And an accident is simulated resulting in a jam, and what you see from the figure is exactly the jam happening sort of halfway through the end of the highway stretch. Okay? So this is basically the heat map or the traffic density map that you see in many transportation systems papers, which tells you what's going on in terms of the segment number and in time, and what is the traffic density on the highway. Obviously, the more yellow the traffic density, the worse it is, which means there's congestion. Okay? So and this figure depicts what's happening without any control. Like on a remote highway somewhere where there's no control algorithm, this is usually what happens, and it takes so much time to actually get rid of this traffic jam. So ideally, what do we want? Ideally, we want this yellow color to be dissipated throughout the figure, or to even be minimized through a smart algorithm. And this is what we want to ideally see. So these are the answers that we we try to answer. There's a typo there. We try to come up with answers to the following questions. Are the proposed controllers, and I have to say that we proposed a couple of controllers, not just one of them. Are the proposed controllers effective against traffic bottlenecks? Are the controllers computationally feasible, or does it take 5 hours to solve this one gain k while the simulation is running? Are the controllers feasible and safe? Like, can an actual driver utilize these components, even if there's no adaptive cruise control or any technology in the car? How should the controller parameters be tuned? Do they require a lot of tuning, or are they tuning free? Can I implement a similar gain on a different highway setup, and will it still work? We've also utilized some evaluation metrics, and the evaluation metrics are as follows. 1, total travel time. So after we implement the controller, is the total travel time reduced, or the same, or increased? Is the total travel distance becoming better? Is the mean speed lower or better, and so on and so forth. Ideally, we want smaller travel time, right? You want to get home earlier, and we want a higher TTD, total travel distance, meaning the control algorithm is able to take people further away if needed, and the higher mean speed. So these are the three metrics that we have optimized for or tested for, and this is what happens when we implement the controllers that we've proposed. We see that there's significant dissipation of the congestion and bottleneck here. Yes.
Just a small question. Why do you have these three metrics instead of, say, just like throughput?
We can. We wanted to be consistent with the papers that we were comparing with, so we used the same metrics that they did. Yes. So this is what it shows. It shows that the jam basically got significantly dissipated in space over a shorter period of time, which resulted in an improvement in the mean speed and an improvement in a reduction in the total travel time, TT, and an increase in the total travel distance. Furthermore, we have actually also implemented this on micro simulations, and we've seen over a variety of simulations and test data that we were able to improve or increase mean speed by 22%, significant increase. We've also compared it with the literature, with the two approaches in the literature, and we've noticed that the proposed approach that we're developing is truly plug and play in the sense that you need very few computations. You basically just need some simple matrix vector multiplication to compute the gain k, which means you can actually implement it in real time, even if there's some delays in communication with the system operator. The controllers also require very little tuning. There's not that many parameters that you need to tune. Whereas in proportional integral based control, you have so many little parameters that you have to tweak with and play with to obtain your solution. The journal paper explains everything in great detail. Yeah.
I'm sorry to interrupt again. Is this a centralized controller or is it operating per
Centralized, yes. Centralized. Another open research question is to actually figure out a way to make that gain k that I showed you in blue to be block diagonal, meaning it's decentralized, meaning it requires little communication, which could be also very important if you want to minimize the communication delay and so on, but the algorithm is still so fast, so the computational time for the gain itself is negligible, so even if you add communication delay, it still won't be big deal, specifically that we're updating the speeds every minute or so, so even if communication is a little slow, or there's a little bit of jam in the network, it wouldn't be a big deal. Future work will actually start testing some of these algorithms on the I-24 motion tested in Tennessee, which I will be talking about shortly. We also would like to obtain a way to robustify the controller against specific sources of uncertainty, so we need to further develop this algorithm theoretically. And we want to investigate some model-free approaches to solve the same problem. Basically, given the data that we're getting from the highway, do I have to derive the physics-based dynamics F, or can I just take the data and do control immediately? Initial results showcase that system identification or data-driven control is still not as good as model-driven one. You don't get the same outcome. If the data is noisy, you get terrible results and so on and so forth. But we're trying to do this, so some bad news for the learning folks, I guess. Also, I'd like to spend a couple of minutes talking about the gigantic testbed that we have in Tennessee. Full disclaimer, I'm not part of it in the sense that I'm not one of the PIs, but it's something that I utilize all the time, and I'm happy that we have that at Vanderbilt and in Nashville. It's led by Dr. Dan Work, who you might be aware of. But basically, we have a giant testbed on I-24 right outside of Nashville, Tennessee, that is the world's most sensed highway. Okay? So it truly is the world's most sensed highway in the sense that the state of Tennessee invested so much in making that stretch of highway highly sensed and highly automated and so on and so forth. And the transportation group at Vanderbilt has done tremendous work in actually taking this raw data that you get from the highway and giving you traffic densities and speeds and so on so you can use in your research. This testbed basically provides real-time traffic MRI and allows for real-time control. And the folks who were working on variable speed limit control implemented the VSL control based on this data and has seen significant reduction in the accidents happening on the highway. So an impressive success story for the group there. And you see what these cameras look like. They look like the following. There's 40 poles, and every pole has 6 cameras. which takes a picture of the cars, and there's a suite of learning algorithms and image recognition and software identification and software recognition tools that basically from the data, from the pictures of the cars, generates densities for you to use in your research or to get real-time data. So this is the website. Please visit the website to learn more about this and to download the data sets. And yeah, I could spend so much more time on this, but please do visit the site and learn more about the work. It's tremendous work, and hopefully soon anyone who actually wants to implement an algorithm can actually take these Simulink files and MATLAB files and start testing your own algorithm on what your algorithm could actually do to the traffic densities on the highway. So you'll be able to plug and play any control algorithm you have in mind and see its impact, so that one of the reviewers in your paper wouldn't say like, oh, you've implemented it on just simple macro simulation model in your publication. We've also worked on other research problems in transportation, and I'll spend a couple of minutes on some of these problems. The first problem that I've worked on a few years ago with some of my students is, where should you place these poles? These cameras that I just showed you, where should you actually place them on highways? Usually in transportation systems, they have a way of arbitrarily placing them every 1 or 2 kilometers. But that sounds a little arbitrary. So if you have a highway that has on-ramps and off-ramps, and there's a certain physics-based model, how can you optimize the placement of traffic sensors, and how many do you actually need? So this paper delineates in great detail how to use control theory and observability in nonlinear dynamic system theory of where to actually optimally place sensors. And the motivation is, maybe you can save a few $1 million by not installing all of these sensors on the highway and installing just a few of them, and have a Kalman filter or any state estimation algorithm that generates what traffic flow would be in places where you did not install the sensor. We've also, this study is basically what I've just explained on CAV traffic control, that has a lot of details and macro simulations, so please feel free to go through it. We've also studied control theoretic properties of stability-related problems to CAV control, which we recently submitted. We also have a lot of work on differential privacy and traffic state estimation. If you want people to share their data, or you want to obtain a heat map, a real-time heat map that anyone in the city could look at, how could you include the concept of differential privacy to solve estimation or monitoring problem in transportation systems? We've also taken some really detailed models in transportation systems, and we solved real-time state estimation problems that sort of build on where to install the traffic sensors, basically reducing the cost of installing sensors and data generation. So basically, there's lots of papers that I invite you to look at if you're interested in this field. Any questions? All right, so for those who are not in transportation now, maybe you find something interesting in this. The second part is about drinking water system problems, specifically regulating water quality and hydraulics. And even if you have no background in water quality or water systems, this will also be a brief crash course on hydraulics and quality. And anyway, a few years ago, I also had no background in any of these areas, so been there, done that. Water distribution network research. The high-level objective of any drinking water distribution system is to deliver adequate levels of pressure and quantity and quality of water to consumers, right? So basically, there's the issue of adequate pressure, adequate quantity, and adequate quality. You want the water quality to be good for human consumption. Major issues in water distribution systems in the US and across the world due to limited natural resources. This might not be a problem in a state like Tennessee, where we get a lot of water and there's a lot of rain and there's a lot of nice aquifers, but it is definitely a problem in areas such as California, Arizona, and so on. We need expansion of these water systems because population is increasing rapidly. I remember when I was faculty in Texas, the biggest project that the utilities back then had were how to build gigantic pipelines to get water from different aquifers 200 kilometers away from Austin or San Antonio. And often this is one of the biggest projects that the city actually votes on, and the people end up paying for over 30 years. So I remember at that time, one of the biggest political issues in San Antonio was that they will increase the water utility bill by like 20%, and a lot of people refused that increase. But this increase was due to the fact that they wanted to build bigger pipelines to get water from different aquifers for the drinking water system. So it's often one of the biggest issues in cities, specifically growing cities, like most of the cities in Texas, the major cities in Texas. Again, monumental challenges for water-stressed states such as in Texas, California, Florida, and Arizona. So this is basically what WDN research is about. To be more concrete, there are two significant areas in drinking water distribution systems that you see hundreds of publications on every single year, and they are quantity and quality. Quantity is basically the process that defines pressure and flow, whether it's steady state or whether it's transient flow. We want to get adequate pressure and flow to consumers across the city. And the major control engineering problem there is how to adjust the pump and valves in real time or every hour to maintain adequate levels of flow and pressure throughout the entire network. Again, the control problem is how to adjust the pump speed and the valve openness throughout the network to ensure that people are getting water with adequate pressure and adequate quantity. The quality problem, which operates at a faster time scale than the steady-state hydraulic problem or the quantity problem, is basically ensuring water is safe for consumption through water quality or WQ proxies. So people in water systems want to establish proxies for water quality, and typically chlorine concentration is a good proxy of whether you should be drinking the water or whether you should be heavily filtering it or throwing it away or boiling it. And what is the control problem for quality? The control problem is adjusting how much decontaminants, like chlorine, you want to inject in the network to decontaminate the network from microbial contamination or from any source of contamination in the network. So there's two very interesting control engineering problems that didn't receive that much attention in the water systems community from a control theoretic perspective, and this is what my group's work is about in this area. Furthermore, there's also the interaction between quantity and quality. Because quality is impacted by the pump speeds and how you adjust and regulate pumps and valves due to how water flows, there's also a very nice integration of the two, which makes the problem even trickier. Some of the technical challenges that are very specific to water systems are, one, flow direction in systems could change arbitrarily. And the models are non-differentiable and nonlinear and non-convex. The topology could be a tree topology, could be looped, so establishing theory that works under different assumptions is difficult. And there's so much uncertainty in terms of the pipe roughness coefficient, in terms of the demand, in terms of sensor noise, and so on and so forth. So what I try to do here with my group is create computational methods for water distribution network operations that focus on quantity and quality, time scale of quantity, the time scale of quality, plus the integration. And ideally, I want these methods to be scalable, robust to uncertainty, and derivative-free. And I do not want to make any assumptions that people have made in the recent past about differentiability of some models, or whether we can linearize these models, and so on and so forth. This is what maybe some of us have learned in a hydraulic class or in a water resources engineering class. These equations model mass and energy balance in drinking water systems. In junctions, and tanks, and pipes, pumps, and valves, basically everything that you see here in blue is linear. Mass balance in hydraulic systems is linear because of the very basic inflow minus outflow is equal to the demand equation, and because of tank dynamics are naturally linear. However, energy balance equations that dictate head loss, head gain in the network are actually nonlinear, all right? And this is what you typically learn in the civil engineering class on water resources on hydraulic models. You learn that the head loss model, the pressure loss model basically is nonlinear, and the mass balance model, which is inflow minus outflow is equal to demand, is a linear model. And this is what formed the basis of our work on quantity in water systems. And this model can be written as a system of nonlinear difference equations that include algebraic constraints. And the control problem here is to adjust the control variables, which are the pump speed and the valves, given that you have a lot of uncertainty from the parameters in the system, the demand, basically D of K, which is in red, and other sources of uncertainty in the system. And what's new in our work here is that we provided new control algorithms that find a way to bound the nonlinearity in a way that you are able to obtain convergence guarantees on when the water flow problem for the hydraulic systems actually converge to a specific solution. And we prove these results in a few journal publications. We've also shown that the control algorithms that we've developed significantly reduce pumping cost, which gives the water utility a lot of incentive to implement some of these algorithms, and the pumping cost is usually very high for the water utility. In fact, in many cities, the water utility tends to be the #1 customer of the electric power utility due to the expensive pumping cost of the system. Moving on to water quality, the water quality models are unfortunately even more cumbersome, so we'll not cover them here. But quality basically depicts how the concentrations of decontaminants, such as chlorine, evaluates in the network. And ideally, you want concentration of chlorine to be between two values in the system. A proxy of water quality, as I said, is the chlorine concentration C of T comma X, where C is the concentration itself in milligrams per liter, and it's in time, so it varies in time and it varies in space throughout the network. The control problem is, as I said, adjusting U of T, the chlorine dosages, and we have an extremely thorough study by one of my PhD students, Salma, who came up with a thorough explanation of how to model the concentration of chlorine in an entire network and built so many different models to capture that. And basically, the ODEs and the PDEs that we use are models that depict conservation of mass and transport and decay of chlorine in the network. We know that there's no analytical solution for that PDE. The PDE is nonlinear, so there's no analytical solution for it. And it was very much unclear which method is best to solve the PDEs. And this is what we proposed here. We proposed a host of algorithms or mathematical models to tell you which method you should be using in different contexts. Also, it was unclear in the literature how to adjust the dosages of chlorine through different vantage points of the network. And we have come up with control algorithms to tell you how to adjust the concentration of injected chlorine. So if there's a microbial contamination, it can slowly subside and water remains healthy to drink. And we have implemented many of these algorithms on on many networks with hundreds to thousands of junctions or nodes and pipes. And we've seen significant impact in terms of contamination risk reduction and cost efficiency. And the basic impact of this work is virtually an MRI that tells you what is the water quality like in an entire city in an urban environment, telling people when should water be, when is it safe to drink the water, when it isn't. These are some of the papers here that were published in some of the water systems journals about how to regulate chlorine in drinking water systems, to how to build a probabilistic method to estimate states in drinking water networks, to some system identification algorithms that show that basically the majority of system identification or data-driven identification models are not good enough. So there's a lot of negative results published in that paper, if you're interested in that, as well as a comprehensive framework to detail how to control chlorine in extremely nonlinear water quality dynamics. Third part, I realize I only have 8 minutes, so I'll try to rush through this. The third contribution here is related to stormwater systems. Stormwater systems are basically infrastructure that has either been naturally built or procured basically to control and mitigate floods, but stormwater systems do much more than just mitigating floods. Stormwater systems also prevent stream erosion while maintaining a very important hydrologic cycle. So, and this work is basically on stormwater systems. We know that urbanization reduces soil infiltration, which increases runoff generation. So basically the water has no place to go due to urbanization. And climate change exacerbates this problem with more intense storms and flooding events. The old solution that cities used to pursue is through the design of reservoirs. They would have a piece of land, they would build a little reservoir or a pond or whatever it is. But this is the old solution, and in many of the urban environments, there's no place to actually build ponds or reservoirs, and it can be too expensive, right? The new solution is basically to come up with control theoretic techniques and control algorithms and pattern models to tell the utilities how to manage current stormwater infrastructure systems with very simple controllers and sensors and a little bit of math. And usually stormwater systems are made up of different subsystems or components. The watershed, the reservoir, and one-way channels. Basically think of water systems as three different graphs connected to each other via outflows or tunnels or pipes and channels and so on and so forth. So in this work, we come up with a system of system modeling to model the overall inputs and the outputs of the system. And we also use ODE and PDEs that are highly nonlinear to depict the physics of stormwater system, coming up with this nonlinear difference equation model with algebraic constraints, where again, the problem is to control U. And in this example, U is basically the gates in your reservoir, or how you're controlling the detention ponds, or maybe where you're putting some green stormwater infrastructure, and so on and so forth, under uncertainty W. In this specific example, X of K are basically the outflows and the depth in the watershed, as well as the reservoir. So there's a lot of really exciting dynamic systems and control engineering problems in this area that we have recently discovered, and mainly due to the fact that a lot of people who work on this discipline are hardcore hydrologists. So system theoretic understanding related to controllability or observability or stability are very foreign to people who work in this discipline, which gave us a lot of food for thought and so on. Also, this problem is filled with uncertainty from water infiltration and rainfall and surface depth. So there's a lot of nice, robust control problems or control problems for systems under uncertainty. What we produce in this work, again, are a set of algorithms that are meant to work for nonlinear dynamical systems under different conditions and under uncertainty. We've actually gotten some data from the city of San Antonio, realistic data from the city of San Antonio and from SARA, San Antonio's River Authority, as well as from the city of Sao Paulo in Brazil, to actually see what would happen if we implement these control algorithms on really accurate models of these stormwater systems. And we've seen a significant reduction in the probability of flood occurrence with substantial cost reduction for the city, and you'll find some of these papers that discuss this. Yeah.
We dabbled from the hydrological side on questions on control. Stability seems to be a problem of these control algorithms. Can you comment on that? Did you face any challenges in stability?
We did not actually. What I meant by stability is it's an interesting thing to consider in the future. Our approach was mainly control. Give me this nonlinear model, tell me what the constraints are, what the cost functions are, and tell me how to solve the control problem as quickly as possible, while being loyal to the physics of the system. So when you approach a control problem from this aspect, you basically get a control signal U, which is adjusting the gates of your reservoir, and you don't theoretically study stability, but we haven't studied it.
Have you seen what kind of fluctuations the gates undergo actually your solutions?
We in the control problem, we ensure that the changes in the gates are very limited. Like you can't suddenly change the gate from that high to significantly larger. So we penalize these deviations, and our solutions, the changes are very incremental and not damaging to the infrastructure itself. Yes.
This is just because we have you here. The data-driven approaches, particularly for data-driven modeling, like you point out, fail a lot here. What are the characteristics of this problem that make them perform so poorly? Are we in a low data regime? Are we what's going on?
I think just the basic system. You're talking about system identification. The issue is we know that even for linear systems, when you add significant level of noise, many of these system identification algorithms fail. Let alone when you do the problem for a nonlinear system and you try to extend these notions of system identification to nonlinear systems. So the fact that a little bit of uncertainty in what your system is makes them just fail immediately. And I think this is the central issue with system identification algorithms. They're not that robust to uncertainty, even when the models are linear, let alone when they're nonlinear or when you're starting from different operating points.
I see. Yeah. And the same is true if you try to use society methods that incorporate notions of the data being noisy or kind of robust society type methods.
The more you change the data, the worse the results become. So, which is, again, it's a good problem to solve, but it's a very difficult problem to solve, which is why I think for the time being, utilizing physics-based models that hydrologist or water quality expert or water chemist has studied for it so long is very important and is probably the right way for coming forward up until new theorists in computer science and learning come up with better methods.
Thanks very much.
Okay, so the last part, I'll take 3 minutes and it'll be done, is about robustifying renewables-heavy power systems. And the issue is renewables. We all love renewables, but they come with their issues, and more renewables means more trouble for future power systems if we don't change the way we control power system dynamics, okay? Unfortunately, the increased penetration of renewables means there's an increased mismatch between prediction and reality, not just in megawatts, but also in percentage points. Because we're adding so much more renewables, that means in 20 years when system operator in New England or New York or California is trying to predict what solar and wind will be over the next hour, and they miss by 2%, this 2% will be much more significant than the 2% that they're missing on today, right? Which means there might be more people who have no electricity for the next hour or so. It's a very serious problem. And we know that by 2050, 56% of electricity will be produced by renewables worldwide, which inches us closer to fuel-free power systems, which is ideally what we want to get at as soon as possible. And this is a figure that shows the increased penetration of solar in time. Scope of this work is basically a new set of control algorithms that are designed mainly for renewables-heavy power systems. What happens if I paid so much money to own a new village or to purchase a new village and I want to build a power system that is mainly comprised of renewable energy sources, solar, wind, batteries, and maybe one small thermal plant. What is the math that I need to manage this system? And the whole idea here is to robustify the power system against worst case uncertainty in renewables. Unfortunately, the old algorithms that power system operators implement in their command and control center are designed for older models for fossil fuel models that no longer work. The cornerstone of a lot of the grid studies and the cornerstone of basically why we get instantaneous power if you flip on the switch is a very ancient control algorithm called the automatic generation control, which is basically what allows you to get power immediately when you flip on the switch. This basic control algorithm is designed for linear systems, not for heavily nonlinear systems. And the issue in power systems is most of these newer models of solar and wind are extremely nonlinear compared to the thermal power plants that are also nonlinear, but not quite as nonlinear as models of solar and wind that involve a lot of power electronics and inverters and so on and so forth. And the control problem here is basically how to adjust the control input U, which is basically how much you're curtailing your solar and wind or how you're controlling voltages in these power systems such that the voltage is regulated, such that the frequency of the grid is regulated, and so on. There's literally hundreds of studies every month. This is a very rich field of research. There's so many studies on this topic. Most of them rely on linearization of the system dynamics and coming up with linear system theory-based method. In this work, we actually get to the nonlinear dynamical system that has a lot of solar, has a lot of wind, and try to find ways to parameterize the nonlinearity and bounding the nonlinearity, and then coming up with a control algorithm. And this is what's missing. What's missing in this literature is a new theory to parameterize nonlinearity and robustify against nonlinearity. And the reason why it's important is it will guarantee robustification of the system in the future when most of the power that is being generated and consumed is coming from fossil fuel-free sources, which could have impact on minimizing blackouts and cascading failures. These are a sequence of papers that describe these contributions, and again, if you're interested in this, maybe you can have a look. Basically, if I were to summarize the talk, it would be development of new computational methods to make today's and tomorrow's infrastructure more secure and resilient and cost-effective using control theoretic techniques that are not too theoretical. I have to emphasize that most of these papers that I've described have a part where we describe the algorithm, and the algorithm could be well understood without even referring to the theory. And we've shown significant improvement in how the system is behaving in different circumstances. Future work will try to study new identification algorithms to do to learn these dynamic behavior of the system better. specifically in solar and wind, a lot of these models might not be as accurate as we would like them to be, so learning dynamic behavior of the models with a lot of data could actually be useful eventually. We're interested also in real-world deployment in transportation systems and so on, and some of my students in the group are also working on dynamic models of climate change and how to understand the varying temperatures in different parts of the planet, understanding controllability and stability properties of climate change models. All of this work was done and designed and written and implemented by this team, so and sponsored by NSF and Tennessee Department of Transportation and my startup package at Vanderbilt. So thank you for coming to the talk and thanks for having me.